Hey folks, got a new topic today called center of mass, which is going to be involved with momentum, and it's probably not one that you would have covered last year in AP Phys 1. So, and then down below there, I've got a diagram of a shape. So imagine this is a shape cut out of like a metal or something like that, and the density of the shape is the same everywhere. It's like a thin metal sheet or something, or even it could be paper or something like that. So, if you had to guess where the center of mass of that object is, like if you, in other words, one way to think of center of mass is where could I balance an object on the tip of my finger? Okay. So imagine you're laying this down on a tabletop, all right, and let's say it's laying on a tabletop, and you had to put your finger at one point to try to balance it. Where would that point be? That's center of mass, okay? Now, in order to calculate center of mass, well, in this object, there's two. There's a horizontal x and there's a vertical y, center of mass. So the equation for that is the xcm is equal to the sum of the mx's over the sum of the m's. Now, you may look at that equation and go, don't the masses cancel? No, and when we do a few examples, you'll see they don't cancel, okay? Now, more generally, you can say RCM equals sum of the MRs over sum of the M's. So that could be X, Y, or Z direction, okay? There is also an integral version of this. So if the density of the object's varying over position or so on, but we're not going to worry about that right now. So a really simple example is, let's say I've got a mass here and an equal mass here, and let's say they are 2 meters apart. Okay, where's their center of mass? Well, you're clearly going to say right there. That's where you could, if they were connected by a very light rod, you could balance the rod on that X. If you put the tip of your finger there. Now, you might say it's 1 meter from the left-hand block, but sometimes we'll give you a reference point like over here, and we'll say from this reference point, where is the X? Well, then it would be 1 meter plus whatever that distance there is. Okay, so that is XCM. That's how to find the center of mass. Now, other things that are related to this. VCM, the velocity of the center of mass, is dx dt, okay, which is the sum of the mv's over the sum of the m's. So for instance, in this picture, let's say this left-hand mass is still, and let's say the right-hand mass is moving at 2 meters per second, okay? After 1 second, it will now be 4 meters from the other mass, right? This will be 2. And our center of mass will now be at the 2 meter mark from the left mass. So how far did the center of mass move? Well, it moved 1 meter. So its velocity would be 1 meter per second. So that's like an example of watching center of mass move. Similarly, the acceleration of the center of mass is dv dt, which is sum of the mA's over sum of the m's, okay? And then finally, the total momentum of a system is equal to the total mass of the system times the velocity of the center of mass. I'm going to use that in the next video for a couple examples. I'm going to talk about like why are we using it that way, okay? Now, going back to our example here, okay, if you need a moment to copy that, make sure you copy that with all the dimensions down. So what we're going to do is we're going to calculate the center of mass in the x and the y direction of that object. Now, here's what I'm going to do. You'll notice that I don't give you masses anywhere, but you do have shapes. And I'm going to just say that each box has a mass of 1, okay? They're all proportional, so we're going to say each box there has a mass of 1, all right? So for the XCM, here's what we do. Okay, we say the sum of the mx's over the sum of the m. Okay, so what I'm going to do is I'm going to split this shape up into a couple of smaller pieces. So I'm going to do one rectangle here on the left, this bottom little rectangle there, and then this vertical rectangle here on the right. So I'm going to have 3 different shapes. And for mass, I'm just going to put the area. Okay, So the left-hand rectangle has an area of 4, and its CM would be halfway across. It'd be at the half-meter mark. Oh, and by the way, I'm going to call this bottom left corner the origin. So I'm going to calculate my center of mass from there. Okay. Plus, I've got this bottom rectangle. It has an area of 2, and its center of mass is right there, which is 2 from the left. So that's a 2. And then plus this right-hand rectangle, which has an area of 3, and its center of mass is 1, 2, 3, and it's going to be right about there. So 3.5. So 3.5 from the right side. And I'm going to divide that by the total mass of the object, which is just 4 plus 2 plus 3. Now, hopefully you notice you cannot cancel the 4, the 2, and the 3 here, right? That's why you can't cancel the m's out of that equation. And when I do the math here, I get 16.5 over 9, which I get 1.83 repeating. And if this were meters, that would be it. So on this shape, if this is 1, this is 2. So it's about here. Somewhere right around there is our x center of mass. All right, let's do the same thing in the y direction. Okay, YCM equals sum of the my's over sum of the m's. Same 3 rectangles, so 4 times. Now, the YCM for this first rectangle is 2 from the bottom, so 2 plus second rectangle had an area of 2. Its CM is a half from the bottom, so 1/2. And the last rectangle had an area of 3, and its center of mass is 1.5 from the bottom, so 1.5. And over the denominator is going to be identical. The total mass of the object is 4 plus 2 plus 3. Its whole area is 9. Now in this case, I get 13.5 over 9, which is 1.5 meters. So that would be along here. So our center of mass is right there. So if you were to lay this down on a tabletop and try to balance it, if you could balance it on 2 very light rods of negligible mass, this is where you would put your finger to balance it. Now notice that point isn't even actually part of the object, and that's okay. The point doesn't actually have to be on the object itself. Really simple example of that. Imagine you have a hoop, okay, like so. Where's the center of mass? Well, it's going to be here. Well, it's not actually on the object, okay? So oftentimes that'll happen. So that's how you calculate where the center of mass of something is. Now, in the last video for this unit, I'm going to talk about velocity of center of mass and also where center of mass moves. And it turns out you can use that idea to solve some pretty complicated problems very easily. So I hope that was helpful, and I'll see you in the next one.